Hi everyone, and welcome to Advanced Microphones Part 2. This is the third and final installment of our microphone seminar series. My name's Steve Tatarunis, and I'm the Technical Support Manager here at Listen Incorporated. So there are just a few topics remaining for discussion in our series, and we're going to wrap those up with today's presentation. We're going to talk a bit about MEMS microphone measurements, and we're going to follow that up with a discussion about microphone arrays. And then we're going to talk a little bit about distortion, in particular intermodulation distortion, and then we'll end things up with a question and answer session. So the first topic on our agenda today is MEMS microphones. And if you were with us for the Microphones Basics seminar last year, you'll recall that we covered MEMS mics in great detail about their construction and theory of operation and so forth. So we're not going to go over that again today, but just wanted to remind you, how quite small these devices are. We have a little image here of a MEMS microphone next to a United States coin, a quarter. So I did want to remind you of the two types of MEMS microphones. First off, the analog MEMS, which has a very straightforward interface to the host circuit. It includes its own amplifier stage, and it outputs a usable signal level with a very low output impedance. And then there's the digital MEMS, where the analog signal from the microphone capsule is converted to a PDM stream. And the advantages of PDM are the electrical noise immunity, the bit error tolerance, and it offers up quite a simple interface in the end. But the thing is, it requires a very specialized test interface. And the test interface needs to convert the 1-bit PDM output to a 24-bit 48 kilohertz PCM stream. And it should have a programmable clock so we can measure the performance of the MEMS mic relative to the sample rate. And it should also have a programmable power supply so we can measure the performance relative to the supply voltage. And it also should have a power supply rejection impairment generator to measure power supply rejection ratio, or PSRR. Now, our partner Portland Tool and Die offers a couple of different MEMS interfaces. There's the DCC 1448, which is used for R&D, and I actually have one here next to me on the desktop here. And there's also the PQC 3048, which is used for production line test. The DCC is much more full-featured, as you would imagine a lab instrument would be, but the PQC has a lot of advantages in terms of cost and size, which make it perfect for the production line. So next I'm going to show you a MEMS microphone test sequence, and you can find this on the Listen website, and it's called Measuring Digital MEMS Microphones. And it's actually a suite of 3 different sequences. There are 2 microphone measurement sequences in the downloadable folder. One uses the microphone substitution method to measure the MEMS microphone, and the other uses the equalized source method. And the third sequence in this package is used to measure power supply rejection ratio performance. And here's a typical MEMS hardware configuration like we would use in a test like this. We have the DCC, we have our computer running SoundCheck, and instead of having a separate audio connect and SC amp interface, we are going to be using the Amp Connect ISC, which combines both the microphone power supply and the amplifier all built into one chassis. And then we have our source speaker here. We're using a Brüel & Kjær artificial mouth. So what I'd like to do now is to demonstrate to you a couple of those MEMS example sequences that we were discussing earlier. And the first one is going to look pretty familiar to you because it's just going to measure the response and the sensitivity of a MEMS microphone. And in this case, I've got my DCC set up over here, and I've got my B&K anechoic box, and inside of the box I have mounted the MEMS microphone that we'll be testing today. And I've already equalized and calibrated the speaker inside of the box, because that's the sequence that we're going to be demonstrating here today, is the equalized speaker method. So let's press play, and then we'll discuss the sequence and the results. So it's a pretty simple display. Up on top here we get the frequency response of the MEMS mic mounted in the box. We can see that our units are dB RE1FS, and then down below here we've aligned the frequency response to 0 dB at 1K and applied some limits to it. And in this case, the sensitivity passes at -26 dBFS, and the response also fits inside of the upper and lower limits here. And the sequence itself is very straightforward. We set up our stimulus, we do a plane record acquisition. We do have a resample step in here because the data coming in from the DCC is at 48K, so we need to downsample that to the sample rate of the amp connect here at 44.1. Once we've resampled the recorded time waveform, we can do the analysis, and then there's a step to determine the sensitivity, and a limit step for the sensitivity, and a limit step for the response, and then everything gets pushed out here to the final display. So it's very straightforward, very similar to the analog equalized speaker method that we demonstrated in our last seminar. So the next sequence I want to demonstrate to you measures the power supply rejection of the microphone. And in this case, we're looking at power supply at 217 hertz because GSM TDM is now often a greater concern, and these are issues that come up when we're using MEMS microphones in communication devices like mobile phones. So when I run this sequence, we're actually using the system custom step in here to send command line executables to the DCC to put it into different states. So the first custom step sets the generator to sine. The second step sets the frequency to 217 hertz. The third step sets the level. The fourth step turns the generator on. And the fifth step turns the generator off, and in between the fourth and fifth step, we're actually doing a record-only acquisition. Well, then we'll take the recorded time waveform, acquire the spectrum through the analysis step here, and then we'll do a post-processing step on the spectrum, where we'll get the average at 217 hertz, which we'll call power supply rejection. And then that will go through a single value limit step with an upper limit only. So when I run this sequence, you're going to see a few windows open and close as the system custom steps are being executed. And then when we get to the end, we'll talk about the results. Okay, so on the XY graph here is the spectrum that we've acquired, and we can see that there is an outstanding feature here at 217 hertz, and the level of the 217 hertz frequency was minus 81.7 dB down, and that passed our limit, which I believe is set at minus 80. So this is a really simple way to check the power supply rejection ratio of your MEMS microphone. And again, all of these sequences are available on the Listen website for you to download and run on your end. It's also worth mentioning that there are a few different ways that we can actually communicate with and control the DCC unit itself, you'll notice that on the front panel we have a touch screen here, and we can enter all of the parameters via the touch screen here. As we just saw in the sequence we just ran, there's also the ability to use the command lines in a sequence by running them from a system custom step. And lastly, the DCC also has its own configurable message step within SoundCheck. So any of the parameters that we can configure through the command line or through the front panel are also configurable through the message step. So we could put a step in the sequence and actually change the state of the device while the sequence is running. So we can change the state of the clock, the sample rate, the VP, the data in state, the coupling mode, the power supply state, the other VP level here, the PDM decimation rate, and whether or not the PSR generator is on or off, and then some of the parameters around that. Our next topic is microphone arrays. And why would you want to use a microphone array? Well, if you were a test and measurement guy like I am, you'd want to use a microphone array because it would improve your measurement accuracy under certain conditions, or it just might decrease your measurement time. And if you were designing consumer products, you might want to use a microphone array because it would improve the performance of your device, such as a mobile phone or a conferencing system or something like that, where the performance would be enhanced by the use of an array. So next I'm going to talk about a few common use cases for microphone arrays, and then we're going to look at a couple of those in a little greater detail. But first, back to test and measurement. I talked a little bit about microphone arrays, and one practical use for arrays are for sound power measurements. And there's two here that we can discuss briefly. There's a 6 microphone array for automotive test and measurement. And then we may use a hemispherical array to do some sort of industrial measurement on an appliance or some piece of machinery where we wanted to measure its sound power. A multi-microphone array can also be used for directional measurements of a loudspeaker. So if you were here for our last seminar, we demonstrated polar plotting using a turntable. But another method for doing this is actually to set up a large microphone array around the loudspeaker, and we can make all of our measurements simultaneously rather than having to make one measurement at 0 degrees and then incrementally rotating around the arc to 360 degrees. So it's an alternative to polar plotting, and it's much faster because we're able to acquire all of our angles simultaneously. The only limitation here is your number of channels. So you really do need to have quite a large array for this, and SoundCheck can support up to 64 microphones, so that should cover most of these applications quite nicely. People use spherical arrays for spatial recordings or spatial measurements. And in consumer products, we may use 2 or more microphones to create a beamforming array. And again, a practical use might be in a phone, a television, or some sort of conferencing system where beamforming is required. So let's talk a little bit about sound power. And there's an automotive application I want to talk a little bit about. And this comes from a paper that was written by Geddes and Blind back in the mid-1980s. And the paper's called Localized Sound Power Method. And in it, the authors propose that a single point microphone measurement lacks sufficient stability to be useful for sound system equalization. And they went on to do a series of experiments looking at microphone arrays, starting with a large number of microphones. I believe they started with 18. And in the end, they found that they could get pretty good accuracy using a 6 microphone array and using spatial averaging from the measurements that came from each microphone. And in the end, I believe they said that they had 90% confidence that this array could provide plus or minus half a dB of accuracy in a third octave measurement inside of a vehicle cabin. And this is still in use today, all these years later. And actually, somewhere down here, I have an example of the type of holder that might be used for such an array. The microphones are spaced about 15 centimeters apart, and generally in the automotive cabin, the array would be located at the user's head position and oriented in approximately a 30-degree angle. And there's another image of one with some microphones actually mounted on it. And sound power in industrial applications, we might have a hemispherical array around the device that we're testing. There is an example sequence in SoundCheck in the how-to examples folder in your sequences folder, and it's called power averaging. So it'll give you a good idea of how you can do this type of measurement using SoundCheck. And here's just an example of what a hemispherical array might look like, a series of microphones that would surround whatever our device under test is. So let's talk a little bit about beamforming. So MEMS mics are very attractive for their size, their affordability, and their low power consumption. And MEMS mics are omnidirectional, and that pattern is useful for many applications. But if directional characteristics are desired, then we can start using multiple MEMS mics for beamforming arrays. And we might include signal processing, such as delay, amplification, and filtering. And these can be applied to the MEMS microphone outputs to boost the desired signal and to attenuate unwanted noise. The thing with beamforming microphones is that they must be closely matched in both sensitivity and frequency response. And MEMS manufacturers tend to do a pretty good job of achieving both of these goals. So if you're buying a MEMS mic from a reputable, well-known manufacturer, chances are that they're going to satisfy both of these requirements. So next we're going to talk about a few different common types of microphone arrays. And the first one is the broadside array. And we typically find these used in televisions or computer monitors where the sound source is expected to be out in front of the device. Broadside arrays use 2 or more microphones, and they're all mounted along the same axis, and they're oriented perpendicular to the expected source of the sound. And by summing the outputs of the microphones will greatly amplify the signals coming from the expected source, since they're all going to arrive simultaneously. And the sounds coming from the left and right of the array, well, those are going to have different arrival times, and therefore it's going to result in a smaller sum. So the sound of interest from the expected source is going to be amplified in the broadside array. Now, signals coming from directly behind, above, or below the array are going to have the same response as sounds coming from the expected source. And here's a little diagram of a simple broadside array. We have our sound source, we have our 2 microphones, and their outputs are summed and then sent out as an electrical signal. Next, we'll talk about the endfire array, and these are typically used when greater directionality is a requirement. The axis of the microphones is aligned with the direction of the expected sound source, and the sound arrives at the second or subsequent microphones after some amount of delay due to their different distance from the source. And the response of the first microphone is summed with the delay compensated responses of the additional microphones. And the on-axis sounds are summed to a much greater degree than the off-axis sounds, and that provides better attenuations of sounds coming from the sides and the rear of the broadside array. These are typically used in handheld devices that are pointed towards the sound source. And here's a little schematic of a simple beamforming endfire array where we have the sound source here. And then we have two mics that are different distances from the source, but on the axis of the source. And then we have some delay compensation here. And then the electrical signal goes out after the delay compensation, and the two microphone signals are summed. And lastly, we are going to talk a little bit about a microphone array that's used for localization. It's used to locate sounds which may be coming from different directions. And in this case, the microphones are located on the perimeter of a circle or of a sphere. And the time differences of the microphone responses is used to calculate the location of the origin of the sound. And a very common application here is something that's used by military and law enforcement to locate the source of gunfire. And here's the schematic of a localization array. So we have 4 microphones around the periphery of a circle. We have the sound coming from one source, and then we have some DSP where all of the microphone signals are going in here. The DSP is determining which one is closest to the sound, and that's how we're doing the localization here. So before I switch over to SoundCheck and do a brief demo of measuring a microphone array, I wanted to talk a little bit about the ATB Automotive Audio Bus, because that's actually what we're going to be using for this demonstration. So we're going to kind of kill 2 birds with 1 stone here. We're going to measure a mic array. We're going to show you A to B, and inside of these microphone arrays over here, we actually have some MEMS mics, so we got a lot of stuff going on here. But a quick introduction to A to B, if you're not that familiar with it. It's a high bandwidth bidirectional digital audio bus, and it distributes audio, control data, and power over a single low-cost twisted pair cable inside your vehicle. So it has a lot of advantages, and I think one of the big ones is that it takes a lot of weight out of the vehicle, and it also can reduce a lot of cost. It supports I2S, TDM, PDM data streams, and also I2C control information. And it supports multiple sample rates and data transfer up to 50 MIPS. So it's a very versatile, flexible, and powerful system. Today we're going to be using the Mentor A to B interface, and it presents itself as an ASIO device inside of SoundCheck, making it easy to configure in the SoundCheck hardware. Here's a picture of the A to B analyzer, and as you can see, I've got one out here on the desktop. And here's a little bit of a schematic showing how one might set this up with your SoundCheck PC, the analyzer, and several slaves. Right now, I've got a couple of slaves here, and each one is going to present themselves as a left-right pair. So we're actually going to be doing 4 independent channels of acquisition when we run our SoundCheck sequence. And then on the output side, this is showing an audio interface and a powered loudspeaker. In this case, we've got our old friend Amp Connect ISC here and a passive loudspeaker. I've already calibrated our little monitor speaker here that's sitting out in front of the arrays, so we're all set with that. So at this point, I'm going to bring up SoundCheck, and I'm going to pop open the hardware settings. And as we can see up here on the input side, we have 4 channels. Let me get these channels arranged a little more cleanly here. We have the 4 A to B ASIO channels here. We have 2 mic arrays, so we have S0 and S1. Those are our sinks, and each one has a left-right component. and we have set these up as digital devices with a 44.1 sample rate and 32-bit depth. And each one of these hardware channels here, the digital channels for the A to B microphones, has a corresponding signal path over in calibration. So I'm going to bring up the Mentor control panel here. I'm going to connect to the analyzer. That was successful. And then I'm going to start the system up with discovery. It's discovered 2 nodes. These are my 2 nodes right here. So that tells me that we're good to go with SoundCheck. Everything's up and running. So before we run our demo sequence today, I just wanted to open up the sequence editor and show you a little bit about what's going on in the sequence. And let me open up the memory list too, because I'm going to want to refer to that as well. So it's a very simple sequence in terms of the number of steps. It's just stimulus acquisition, 1 post-processing step, 1 analysis step, and a display. But we are doing some interesting things here that show off the power of SoundCheck, particularly under measurement conditions like this, where we have multiple input sources. So we start out with our stimulus file. It's a simple sweep from 10K down to 100 hertz with 12th octave resolution, and we're applying equalization to our source speaker that's here in the Brüel & Kjær anechoic box. Now here's what things get interesting in the acquisition step. And as you can see, I've got my 4 signal paths set up for the A to B mic arrays that I have over here. And I'm giving them custom names. We're going to call them RTW, nice and short. And I'm also going to append the signal path names to the waveform names. And we can clearly see that over here in the memory list. And what I've done, I've taken the 4 waveforms that are going to come out of this acquisition step, and I've placed them in a group. And the reason I've done that is because now I can take all 4 of these waveforms and batch process them through our frequency shift step. And the reason we're frequency shifting here is because we're using 1 device for playback and 1 device for recording, the Amp Connect and the A to B analyzer. And even though they're both operating at 44.1 kilohertz sample rate, there's a possibility that they have slightly different clock rates. And the frequency shift step is going to correct for any slight discrepancies between clocks between the 2 devices. So I can put all 4 of these waveforms into a group, point to them as operand A, tell the step to automatically calculate their sample rate, and then I'm going to use the stimulus waveform as the reference waveform. So now we can process all 4 of these waveforms in a single step. And once again, the output from the frequency shift step, I'm going to take those 4 waveforms, place them into a group so we can do batch analysis. And that's what's going to happen over here. On the Waveforms tab, I have a custom group. I've got my 4 frequency shifted waveforms. And when the step is applied, we'll get analysis of all 4. And once that's done, we'll simply put the results up on 2 displays. And there we have our final display. One of these comes out very well matched, while the other one seems to have a little bit of a mismatch through the midband here. It could have something to do with this setup here. It's not really the best configuration for a good microphone measurement, but I wanted to have all of the equipment out in the open here, so certainly some reflections, and we're probably seeing it down here on this bottom XY graph. But the top ones look like they're pretty well matched. We can see that there's a little bit of a rising response up in the top end. And the second channel kind of shares the same, the second microphone pair shares the same type shape, but microphone number 2 just isn't quite in sync with microphone number 1 for whatever reason. So our next topic for discussion is intermodulation, or IM distortion. And the thing is that microphone distortion is very difficult to measure. Using the standard methods that we've shown you here in these seminars, the source speaker itself is likely to have higher distortion than the microphone under test. So what can we do when we can't make traditional THD measurements on a microphone? There's an alternative, and that's using intermodulation distortion measurements. So for the example that we're going to discuss today, intermodulation uses a master tone, which in this case is a fixed tone at 100 hertz, and a slave tone, which is a sweep from 10 kilohertz to 224 hertz. And the two tones are played back at a 4:1 ratio. It's also very important that separate speakers are used for the playback of the stimulus here. So for example, we'll play the master tone through a subwoofer, and the slave tone, the sweep, would be played through a full range speaker. Otherwise, if we played this through a single source, the speaker would produce intermodulation distortion of its own. So very important that we use two discrete speakers for the playback here. And we have a sequence for this on the Listen website. It's called Intermodulation Distortion Sequence. So you can feel free to head over to the website and download that after our presentation today. And just a heads up that we're going to have a future seminar on distortion where it's going to cover a whole bunch of different distortion methods in much greater detail. So we won't do a demonstration of this today, but I will show you just a brief schematic of a setup that could be used for this type of measurement. We have our SoundCheck PC. We have an amplifier to power our full range speaker. We have an Audio Connect interface, and this assumes a powered subwoofer, so we have a line output to the powered subwoofer, we have a line out to the SC amp powering the full range speaker, and then we have our microphone under test out here in front of the speaker array. And the example that we show in our sequence note has a final display that looks like this, where we have the fundamental of the microphone under test at the top here. We have the IM2 and IM3 components shown on the display, and then down here on a separate XY graph, we have the total IMD. So once again, this sequence is available on our website, and there's actually a nice link in the sequence note that accompanies this sequence to a paper that Steve Temme wrote back when he was working at Brule and Care on distortion measurements, and there's a lot of great stuff in there. So feel free to check that paper out as well. So before we wrap things up today, I wanted to answer a couple of questions that came in on the survey forms from our past seminars. And the first question is pretty common, and it's how can I apply a weighting to a noise floor spectrum? And that's something you might commonly want to do when you're measuring microphone noise, input noise, things like that. And the thing is, there isn't necessarily an A weighting post-processing step in SoundCheck, but there's a very, very easy way to do it. And I wrote a small example sequence here to show you just how to do it. So let's open up the sequence editor and take a look at what's going on. So the first thing that we're required to do is actually recall an A weighting curve into the memory list. And we do that with this recall step here. And there is a DAT file in your SoundCheck data folder called A, B, and C weightings.dat. And when you point to that, you'll see that there are indeed 3 weighting curves in here. And today we're only interested in the A weighting curve. So we're going to highlight that and not select the other 2. And that way we don't clutter up our memory list with unwanted curves. So we'll just recall the A weighting curve. And aside from that, it's very straightforward. We're going to do a brief record-only step. We're going to do a spectrum analysis of the recorded time waveform of that record-only step, which is just recording the noise floor of our direct input. We have a shorting resistor on the input here. And once we have the spectrum, here's where we do the actual A weighting. So we'll use a arithmetic step where we're doing linear multiplication, and the spectrum's operand A, and the weighting curve is operand B. And I put a custom name down here for spectrum A weighted. So that's all you really need to do. Once you have your spectrum of interest, you just do some arithmetic on it, multiply the spectrum by the weighting curve using a linear multiplication operation. So let's just run the sequence and we'll see what comes out. And that's what we would expect. We have our unweighted spectrum here in blue, and then with the A weighting applied, we come up with this orange curve. And there's one more question I want to get to today. And that is, can SoundCheck measure microphone phase and polarity? And the answer is yes, it can absolutely do that. And we'll show that to you now. So what I'm going to do is I'm going to open up the standard microphone sequence. This is the one where we use calibrated and equalized source speaker. Everything's all set up in the Brule and Care box here. It's already been equalized. And I'm going to run the sequence one time. So this will probably look familiar to you if you've been with us for some of our past seminars. Up here we have our microphone fundamental response, and then down below it's the fundamental that's been aligned to 0 dB at 1K. So let's talk about the phase first. And the thing is, in SoundCheck, phase is always available. It's just hidden from view. And if you want to look at the phase on an XY graph, you right-click on the graph, and there's an option down here to view the phase. So there's the phase response of our measurement. If we want to, we can go in and hide the magnitude and just show the phase here, or bring the magnitude back. So that's very simple to do. So there's phase. And the other question was about polarity. And the easiest way to go about this is to go into your analysis step. And on the delay tab, there's a checkbox here for polarity. And this is a simple polarity method. And what it's going to do, it's going to return a single value to the memory list. It will return a 1 if the polarity is positive, and it will return a -1 if the polarity is negative. So it's very easy to set a single value limit on the polarity value. So I'm going to click Apply here and go over to my Values tab. And now I can see that I have a value for polarity. And in this case, we're mostly concerned with the Y value here. It's a 1. That tells us that the polarity of the microphone is positive. So now we can add a limit step to our sequence. Have the limits group open. I'll go single value, lower only, and I'll stick that here. Point to my polarity value, and I'll set my lower limit as 0. So if it's 1, the step will pass. If it was -1, it would fail. So now I've got a new result in the memory list here. And actually, let's give that a name. More specific. And there's polarity. Drag it over here. And there we have our third result. So as you can see, it's very easy to measure phase. It's always there. It's usually hidden. If you want it just to review, come in and right-click on the plot area and select phase. And then the polarity value can be output by your analysis step. So hope that answers a couple of questions for you out there. And that's it for the past Q&A. So that concludes today's presentation and our series on microphones. So thanks again for attending, and we'll see you all next time.